Welcome everyone to this session. In this session, we'll talk about virtualizing OPTEE with Secure Partition Manager, that is happening running at Secure EL2. Let me introduce myself. My name is Arunachalam, working in open source software group at ARM. This will be a joint presentation. With me, I have Jens Wicklander from Lenaro. Today, we will cover about what ACL2 feature is and the software that it runs on ACL2, and a bit about ARM FFA, and then we'll talk more about the OPTEE driver changes in the Linux kernel, as well as the OPTEE-OS changes in the secure world to make it FFA aware, and as well as to add SEL2 SPMC support. So virtualization in secure world. ARM 8.4 architecture introduced a new exception level in the secure world called SEL2. This is similar to the EL2 exception level in the normal world. How EL2 exception level provides capability to run multiple virtual machines on top of hypervisor. Similar functionality is provided in the secure world, whereas multiple secure partition can be isolated from each other by using a hypervisor like functionality in SEL2 exception level. The isolation is achieved by two-level table translation by VA to IPA, and then IPA to physical address translation. And the software that the software runs on SEL2 is Hafnium hypervisor. Initial implementation of Hafnium was only on normal world. ARM has added support to run Hafnium in the secure world, and also added FFA adoption to Hafnium. Talk about what FFA is about. It stands for Firmware Framework for A Profile. This is this is a specification developed by ARM and contribution from Google, Silicon vendor, and as well as multiple trusted OS vendors. This specification standardizes the communication interface between the endpoints. Mainly the communication happens from the normal world to the secure world. That communication has been standardized by these specifications, and it also leverages the SEL2 of the hardware features like SEL2 and SMMU stage 2 translation feature in SMMU, and as well as the virtual gig. The main terminologies that Firmware Framework introduces is about the SPM, which stands for Secure Partition Manager. The Secure Partition Manager is composed of two components. One is the Secure Partition Manager Dispatcher and the Secure Partition Manager Core. The Secure Partition Manager Dispatcher responsibility will be to forward the calls that comes from the normal world to the SPMC component that runs in the SEL2. The, the spec supports running SPMC either in SEL1 or in SEL2. In the image shown over here, the SPMC here runs at SEL2, and in this configuration there are multiple SPs that are shown above. It can either be a SEL1 SP, or it could be a SVC mode, or it could be a SEL0 secure partition. For our case, we'll be talking about SEL1 SP, which in this it will be OPTEE, and SEL2 SPMC, which will be Hafnium, and the SPMD component, which is in EL3 firmware. The firmware framework extends the SMCCC as a transport for sending and receiving FFA messages. So we'll talk about the changes that are done in OPTEE driver. So first thing is in the EL3 there is a trusted OS specific dispatcher named OPTEE. Now that has been replaced by SPMD, which is a generic dispatcher. If any trusted OS adopts FFA, then the trusted OS specific dispatcher can be replaced with this generic dispatcher. The functionality is similar to what the OPTEE dispatcher would be doing. Mainly, it handles the world switch routine, save and restoring context, and also it forwards the prior OPTEE dispatcher would be forwarding SMC calls. Now the SPMD will be forwarding the FFA calls from the normal world and secure world. Talking about the initialization, the BL2 bootloader 2 loads the SPMC component and the secure partition images as mentioned in the FIP image of the trusted firmware. Like the SPMC, that there has to be resources mentioned. What memory region the SPMC will be using, and what are the memory regions where the secure partition, and what are the devices the secure partition will be using, and all these are mentioned through manifest files as shown over here. This is the SPMC manifest file. You can see uh, the compatibility string where which aligns to FFA specification, and it also has the SPMC ID, the major and the minor version where to which the specification it implements, and also the entry point and the load address of the SPMC component. And it also lists the secure partition that needs to be loaded as shown over here. It's the VM, whether the secure partition is FFA aware, and what is the name of the secure partition, and how many vCPU it consumes. These manifest files are combined together in the FIP image, which will be consumed by the SPMC during the init phase. Coming to the Linux kernel side, uh, based on the ARM FFA specification, there is a generic driver implementation in Linux kernel called ARM FFA driver. What the main role of the ARM FFA driver is to expose the FFA specification as a transport in the Linux kernel, like FFA transport. It provides a generic interface to multiple T subsystem inside the kernel, and exports in kernel APIs to the T subsystem. In this case, it will be OPTEE, so that later it can be consumed. The FFA device driver follows the Linux kernel device driver model, whereas the FFA ARM FFA bus is represented as a logical bus over here, and there are devices which are attached to this. Like every secure partition will be identified as a device, and the corresponding driver routine will be probed, which is the driver over which is shown over here. And the transport of the message happens over the SMCCC standard. It could be either a HVC conduit, or it could be a SMC conduit. During initialization, the ARMFA driver is responsible to load or to probe the secure partition based on the UID. Basically, it does partition get info to the secure world, and it fetches the secure world the partition's ID, and registers with the device in the Linux kernel subsystem, so that later OPTEE can use that ID to send and receive messages. It implements FFA spec 1.0. The main functionalities that it provides are sending and receiving direct messages, memory sharing, and memory reclaiming functionality. So moving on, coming to the OPTEE driver, the main change that has been done in OPTEE driver is to have FVA transport support for OPTEE driver. Prior to this, OPTEE used to have SMC based communication. Now those SMC based calls are replaced with FFA calls. There are three main categories. One is the client FFA ops, and supplicant FFA ops, and the OPTEE core FFA ops. Uh, this, as the name suggests, OPTEE client FFA ops are used by the client application in the normal world. The supplicant FFA ops are used by the T supplicant, and the core FFA ops are used by the RPC and message batching subsystem. So this the function routine or the pointers in this subsystem are now points to the FA interface as shown over here in this diagram. Like normally the call that comes from the client apps to the generic T API, and following to the Linux kernel through the generic T subsystem, and from there it reaches the OPTEE driver. Within OPTEE driver, all the subsystem within OPTEE driver uses the FA interface. The FFA interface is during the init time, it would have probed the FFA ops, and through which the messages are passed down to the FFA driver in the Linux kernel. The FFA driver will be responsible for uh, assigning the FFA API particular API numbers to it, and forwarding the call to the layer below it, mainly the EL3 SPMD dispatcher. From here, the dispatcher will be forwarding the call based on the destination is the forwarding the call directly to the SPMC component, and SPMC component based on the destination ID will route the call to any one of the secure partition available. The direct message send and receive related operation will be directly forwarded to the OPTEE-OS that is running in the secure world side. Memory sharing related APIs, the Hafnium will handle it. Mainly, it will create a stage 2 translation entry for the page that is being uh, for the non-secure page that is being provided by the uh, as argument that is provided through the FFA ABI memory sharing ABI calls. As shown over here, during the OPTEE driver initialization, the OPTEE FFA probe routine is called. It will initialize the FFA operation by fetching the operations directly from the FFA driver, and it also checks the version compatibility, whether what is the spec that is implemented by the OPTEE-OS that is running in the secure world side, and it also exchanges the FFA exchange capabilities. And the probe and detection and loading of the OPTEE driver all happens through the device tree entry. This UID will be the SP's the secure partition UID and what version it is compatible to. This entry will be used by the ARMv8 driver, and based on the UID, it will probe each driver in the Linux kernel. So moving on, we'll talk about ARM driver FFA calls. Mainly, it is categorized into ARM FFA blocking calls and ARM FFA yielding calls. The blocking calls are used during the initialization phase. It while it executes the FAQs are disabled, and the functional and the return arguments are sent through the registers. Whereas when it comes to yielding calls, when a call is made, when a yielding call is made to the secure world, uh, a thread is assigned in the OPTEE-OS to run this particular command. It could be either to run a specific T client related API, or it could be to register or unregister a shared memory. And the OPTEE yielding calls, when it returns back, it could return back with this any of this return argument. Based on the return value, the OPTEE driver handles whether to retry a particular command or to handle a RPC command sent by the OPTEE-OS. Here in this diagram, it shows the flow of the OPTEE FFA call from the T subsystem to the SPMD layer. So you can see TIOC invoke is a generic command which is widely used. Here, the T command holds the command that needs to be passed to the OPTEE. It could be a login, or it could be open session, or it could be a socket related API. And this is packed in OPTEE message, and later on the OPTEE driver assigns OPTEE FFA yielding call with arguments, and it adds the cookie. This cookie is a global handle assigned by the SPMC component. Once this is once this is set, the call is forwarded to the FFA driver by doing a sync send and receive. The FFA driver adds the source VM ID and as well as the destination secure partition ID, and it sets the FFA function to be a FFA message and direct request, and forwards the call through SMC to the SPMD component. The SPMD component saves and restores the secure world state and forwards it to the SPMC. Once the call returned back from SPMC, SPMD does a ERIT, and that way the control comes back to the FFA driver. Now the FFA driver looks at the OPTEE FFA response code, and accordingly it sets the argument and returns back to the OPTEE driver. It could either return with a FVA busy or could be a FVA success. In case of a busy, which means there are no available threads in the secure world side to execute this particular command, then it waits for a thread to be available and the command will be retried. If it is a FFA success, then it follows, then it goes ahead and checks for this return value. What are the return values that is coming as part of this yielding call? Based on that, the RPC command is executed. The support for FFA drive transport support in OPTEE driver is a work in progress. This macros might change in the upstream version. Once the RPC commands is handled, if at all the RPC command has to be, then later the control passes down to the back to the T subsystem. The OPTEE-OS support for FFA and SEL2 SPMC support will be discussed by Jens. Over to Jens.
Thank you, Arun. Here I'm going to talk about the OPTEE side of FFA and also running OPTEE with a hypervisor at Secure EL2. We have support for running OPTEE with FFA, but without a Secure EL2 upstream. This is experimental support and should be considered to be work in progress. Without the 3 patches, we also have a working setup with Secure EL2. With FFA, we always have an SPMD at EL3, and with OPTEE in the picture, the SPMC is placed in Secure EL2 or Secure EL1. So when configuring OPTEE for FFA, we only need to tell where the SPMC is to be placed. During the rest of this presentation, I will focus on the case where the SPMC is placed at Secure EL2. Booting of OPTEE is similar to before. We have a start function which is entered by the primary CPU. During initialization, the SPM is informed of the entry point of the secondary CPUs. The secondary CPUs are then initialized by entering CPU on handler. OPTEE-OS FFA message wait loop. An FFA message is sent with the HVC instruction, and with this, control of the CPU is handed over to the SPMC. Execution in OPTEE is resumed at the next instruction when a new FFA message is received. The state that we had before the HVC is restored, except that X0 to X7 are updated with a new message. So we have a message loop similar to the example here to the right. The loop is entered the first time when we signaled the CPU has completed boot with FFA message wait, and not left again unless we have a yielding request. Yielding requests are the ones that may do remote procedure calls or RPC. Those requests are the only ones that can be interrupted by a non-secure interrupt. When doing an RPC, we may very well return a different CPU, so the state is saved in a way that it can be resumed by any CPU. OPTEE-OS messages. All the FFA messages received by OPTEE are run to completion, but a yielding behavior is built on top of 2 messages, send-direct-rec and send-direct-resp, so that a request being processed by OPTEE can be temporarily saved before doing a send-direct-resp and later resumed by another send-direct-rec. The return value in register V3 of send-direct-resp indicates what kind of return OPTEE is doing. If we are done, we expect to be called the next time with a new call with arg. Else, we expect to resume the ongoing call with the call resume. In the example to the right, you can see a sequence where a call is both preempted and requests an RPC command before being done. OPTEE-OS Secure EL2 SPMC memory sharing. Sharing memory from normal world to secure world is a 2-step process. First, the memory is registered for sharing with the SPMC using a FFA mem share. With this call, With this, the caller gets a global handle, or a cookie, as we call it in OPTEE. This is in the system a globally unique identifier of that piece of shared memory. The next step is to share this cookie with OPTEE. This is normally done with a yielding call with this cookie as one of the memory parameters. When OPTEE sees that this is a new cookie, it will call FFA mem retrieve rec. When this function returns, the memory can be mapped in OPTEE. In the example to the right, you can see a typical sequence used to share memory. Relinquishing or stop sharing memory is also a two-step process. When started from the normal world. There's first a call to OPTEE FFA unregister SHM with cookie as parameter. If OPTEE isn't busy using this memory, it will make a FFA mem relinquish call to SPMC to release the memory and then return success to the normal world. This way of dealing with non-secure memory prevents OPTEE from accessing any non-secure memory that isn't shared. In fact, the same applies to secure memory. OPTEE has only access to the memory that the SPMC has granted. Thank you. And now over to Arun.
Thanks, Jens. Now we'll have a demo on FEP with OPTEE, FVA Transport, and SEL2 SPMC support. Here I have a FEP booted with OPTEE as a secure partition along with Hafnium. These are the initialization messages of Hafnium, and it loads OPTEE with 8 vCPUs, and these are the OPTEE boot messages. And here you can see the OPTEE register the secondary core entry point with SPMD, and later once the Linux kernel boot, the vCPUs are initialized in OPTEE. Coming to the Linux terminal, we can see the ARMv8.4 bus under sysfs, and this is the device of which is OPTEE Secure Partition and the corresponding driver to it. Now we'll run some sample test cases. As you can see here, the messages that are passed from SPMD to SPMC, and these are the FFA ABI calls, along with the arguments passed in the registers. This brings us to the end of this presentation. Thank you for your time and attention. Thank you.